Okay, so let's look at another distribution. We're going to look at what's known as the normal distribution. If x is normally distributed, then its PDF is given by f of x equals this on a domain from negative infinity to infinity, where mu is the mean and sigma squared, or is the variance, making sigma the standard deviation. And we would write that x is distributed as a normal distribution with parameters mu and sigma squared. The parameters for a normal distribution are written as mu, the mean, and the variance, not the standard deviation, which we're most used to using, and actually what we'll use in calculations throughout this section. Now, you might be looking at this equation going, oh my goodness, you actually mean that I'm going to have... No, absolutely not. You do not need to use this function right here. It's not necessary. Technology provides us with a tool to analyze this function very nicely. For the curve y equals f of x, we just showed you the equation. The normal curve, it's symmetric about the line x equals mu. So this is a symmetric distribution. As x approaches infinity and negative infinity, the normal curve approaches the x-axis. It's asymptotic. And all of the f of x's are greater than 0. And since this is a probability density function, the total area under the curve must be 1, meaning the integral from negative infinity to infinity, f of x dx is equal to 1. So I can find areas under this curve using integral calculus. And you're, again, going back to that equation saying, really? Really? I don't think so. And you're right, you don't need to. This is all done using technology. For high-level mathematics, yeah, you might do this just for fun, but you don't need to. And what this is showing us is that more scores are close to the mean than far away. It has a bulge right here close to the mean. This is where the bulk of the scores would show up. And out here, there isn't very much area. There's not very much data. And a lot of people will call this a bell curve. And there is something known as the empirical rule. If data is normally distributed within one standard deviation of the mean, going one standard deviation either way, and we'll talk more about what this means in a minute, but there's approximately 68% of all the data will lie one standard deviation away from the mean. Approximately 95% of all the data lies within 2 standard deviations of the mean. So from there to there, this represents 99 or 95% of all the data in the distribution. And if we go out 3 standard deviations away from the mean, now we're talking darn near 100%. It's 99.7% of all the data will lie within 3 standard deviations of the mean for a normal distribution. This is always the case if data is normally distributed. It's a special distribution. It doesn't hold true for everything. So let's say that the mean for this distribution is 8, and the standard deviation is 2. What this empirical rule tells us is that between 6 and 10, 68% of the data will be there. Between 4 and 12, we should expect to see 95% of all of our data. Notice I'm going 2 units for each one of these intervals. That is 1 standard deviation. And 3 standard deviations below the mean would be 2, and 3 above the mean would be 14. And if this is normally distributed data, I should expect that 99.7% of all the data will be in between 2 and 14. Let's use this. So chest measurements of 18-year-old male footballers are normally distributed with a mean of 95 centimeters and a standard deviation of 8. Find the percentage of footballers with chest measurements between 87 and 103 and 103 and 111. Okay, so I'm going to draw a picture. I'm going to draw a bell curve. It says it's normally distributed. That means the mean will be right in the middle. That's 95. 1 standard deviation away, that is 8 centimeters away, that's going to be 103, and 87. 2 standard deviations away from the mean. That's going to be 111 would be 2 standard deviations above, and 79 would be 2 standard deviations below. And then 3 standard deviations, that's going to be 119 and 71 for this. So I want to know the percentage between 87 and 103. So that percentage of data, that's 1 standard deviation greater and 1 standard deviation lower. And if we look back at our empirical rule, we should expect 68% to be within there. Between 103 and 111. Okay, so how do we do this? Well, we could just look back at this. We see that it's approximately 13.59, but we know that from there to there is 95%. And from here to here is 68%. So if I were to subtract those two, I would find the blue plus the purple. So if I take 95 minus 68, that's going to be 27%. And that's distributed between those two spaces, but I only want the blue part. I only want right here, so I have to take the 27 and chop it in half, and that is going to be 13.5%. I really don't, if you know me, you know I don't believe in memorization. I don't believe in memorizing all these different percentages in here. It's a big waste of time. If you're going to memorize something for this, make it these 3 numbers right here that I just highlighted blue. From that, you can reason out what all of these others are. Next thing to look at is something called a z-score. A z-score is found by taking a data value minus the mean divided by the standard deviation. So, for instance, if I want a z-score for 210, I would do 210 minus 200 divided by 10, and I get 1. If I wanted a z-score for 200, 200 minus 200 divided by 10, or 0. So the z-score for 200, the z-score for the mean is 0, and that's always going to be the case. And the z-score for 210 is 1. Notice how far away 210 is from the mean. It's 10, and the z-score was 1. What does z-score measure? Z-score measures how many standard deviations you are away from the mean. That's what it is. And that should make sense that the z-score for the mean is 0. The mean is 0 standard deviations away from itself. And what a z-score does is it's also called a standard score because it standardizes data. So this bell curve here, mean is 0, and I converted the 200 to a 1. What if I convert this bell curve to z-scores also? Well, 5 is going to become 0, and 7 minus 5 divided by 2, that's 1. And these standardized scores, these standardized normal distributions, look identical because I'm using these standard scores. These z-scores allow us to compare data from data sets that are slightly different, that have a different mean and a different standard deviation. Turning them into z-scores makes them comparable. That's something to remember. Okay, so let's do some problems. We've got 3 examples to go here. And get your calculator handy because we're going to use it today. So we have rugby players normally distributed with a mean of 179 and a standard deviation of 7. And I always recommend drawing this normal distribution and finding what area you're looking for. Remember, the area under this curve is 1. It's representative of probability. So I'm trying to find the probability that the player was at least 175. So if I can find the area 175 or bigger, that's going to be my probability. If I take 175 and subtract 179 divided by 7, we get negative 4/7. That's my z-score. It's not a nice whole number of standard deviations away. The empirical rule is not really something that I can apply here. Notice the z-score is negative because 175 is smaller than the mean. This is where technology is going to be our friend. So here's what I'm going to do. Menu, probability, distributions, normal CDF. And this is the calculator way of saying negative infinity. Negative 9 times 10 to the 999th. It's negative, huge number. If I wanted to say positive infinity, I would simply get rid of the negative and it would be 9 times 10 to the 999th. If you can hear in the background, you might hear my son. He's just really excited about the normal distribution. He loves this stuff. It's great. So, upper bound. Well, lower bound. I don't want lower bound to be negative infinity. I want lower bound to be 175. Upper bound, I want infinity. 9 EE. Now, mean, I know that the mean is 179, and I know that the standard deviation is 7. I press enter, and I find that 71.6% of all rugby players would be at least 175 centimeters tall. So how do we do it for the second one? Well, let's draw our distribution. 179 is still in the middle. Standard deviation is still 7. 170 would be down here. That's 9 away from the mean. Empirical rule isn't going to help over there. 190 is over here. That's, well, 11 away. That's not 1 or 2 or 3 standard deviations away. We're looking for that area. I want you to pause the video right now and put this into your calculator and calculate this probability. Hopefully you're going through these same steps, or you already went through these same steps. 170 to 190, mean is 179, standard deviation is 7. Okay. We have 84.3% to 3 significant digits. So most of what you're going to do when you see normal distribution, you should have calculator ready, unless it fits with this empirical rule. And that's where I'm going to leave you in this video. We're going to come back to the next 2 examples in the next video that you're going to watch. Second to last example, here we go. So we know that 80% of the history candidate should pass the final examination. The exam results are normally distributed, mean of 62, standard deviation of 13. What's the lowest score necessary to pass the exam? Alright, so we know it's normal. We know that X is distributed normally with a mean of 62 and a variance of 169, or 13 squared. So we have a bell curve with 62 right here, and we know that 80% are going to pass. Well, the failure spot would be down here. The question is, what's that score? We don't know, but we do know that is 80%, and by default this is going to be 20%. So what we can do is we can use the inverse of the normal CDF. If we go to our GDC and we go into our distributions again, you will notice that one of the choices is inverse normal. We use this when we know a percentage and we want to find information out about the data. The normal CDF is used when we know the data and want to find a percentage. Please keep those two things straight as you're going through this. So what's the area? When it asks for area, it's always asking for the area to the left of the data value that you are trying to find. So we don't use 0.8, we would use 0.2. And the mean was 62, and the standard deviation was 13. We do our calculation. There's our score, 51.05. Using our inverse normal. So if we go to 51, we're going to assume that the test scores have to be whole numbers. But if we go to 51 and give that as our answer, we would be slightly bigger than 80% passing. So what we would do is we would round to 52 as the lowest passing score. Next example. We have scallops. Some people love them. I hate them. Can't stand scallops. But we have an adult scallop population. It's normally distributed in terms of their weight. So our random variable is normally distributed, but we don't know the mean. We do know the standard deviation is 5.9. So our distribution could be written this way, 5.9 squared. I'm going to draw my bell curve. In the middle, well, we don't know that. That's mu. We know that 15% weigh less than 58.2. Where am I going to put that 15%? What's going to be down here? 15% are less than 58.2. So here I know a percentage and I'm trying to find data. We're going to use inverse normal. So into our GDC we go. Area would be 0.15. That's the area smaller than the data value that I know, but I don't know the mean. So I can't put a value in right here. So what we do in this case, when we're looking for mean or standard deviation, we leave these as 0 and 1. We're going to treat these as z-scores now. When I do my inverse normal for this, I'm going to get the z-score that corresponds with the 0.15. So my z-score is this. So I can come back to my problem and I can write down z equals negative 1.0364. And it's negative, which is good since our data value is smaller than the mean. And if we go back a few slides, how do we find z-score? We take the data value minus the mean divided by the standard deviation of 5.9. And this is an equation that we can solve. And we multiply by 5.9, we shuffle some things around, we move things from one side to the other, and we get that the mean is approximately 64.39 or 64.4 grams. And there we go. So this is where I stop. This is where I leave you. I hope you enjoy this section as much as Mason does. He's a normal distribution freak, so enjoy.